Hey everybody, it's Beej with Lambda School. In this video we're going to talk about bitwise operations. The goal of this video is to learn what bitwise operations are and how we can use them, some of the ones that are available, and then learn how to apply them to multi-bit numbers as well as single-bit numbers. Now we're used to Boolean operations that work on true and false values, but these bitwise operations by comparison work on numeric values. It's going to be very similar to what you already know. You've used and, or, and not with Boolean values in if statements and while statements and so on. But now we're going to use them on numbers. We know that computers use ones and zeros deep down, and 0 conveniently can represent false and 1 can represent true. And if we've decided that that's the case, then we can use and, or, and not, and so on. So we'll learn how to do this in a numeric sense. And then we'll also learn some other operations that you might not have used before, like exclusive or, nor, and NAND. A general rule going forward is that if you're operating on Boolean values, true or false, then you're going to want to use the Boolean versions of these operations. And these are the ones you've used in the past, like double ampersand for and, or double pipe for or exclamation point for not. You'll want to use those on Boolean values like true and false. But if we're working with numbers, then we want to use the bitwise versions. These operate a bit at a time, and they will get the same job done except numerically. So let's take a quick look and see what we have for these different operations. First of all, we're going to look at what's called a truth table. And this is the truth table for a bitwise not. You're used to not being an exclamation point when dealing with Booleans. And this does the exact same thing. Remember, 0 represents false and 1 represents true when talking about these numbers. So we have in the left column of this truth table the value 0 for A. And then we see in the right column the value for not A, which is 1. Likewise, if A is 1, then the value for not A is 0. Not is what we call an inverter, because it inverts the bit. It changes it from a 0 to 1 if it's a 0, and it changes it from a 1 to a 0 if it's a 1. And this is exactly the same as how your Boolean not works as well. You're used to saying not true, you're used to that being false. Not false, you're used to that being true. This is the same thing, except again, we're doing it with numbers. So for a quick demo, we can have a look here at our not operator. The not operator in most languages is a tilde. Now, this comes from C, which may have gotten it from somewhere else. I'm not actually sure. But this is the same in most modern languages, if not all of them. So what tilde does is it changes the value from a 1 to a 0 or a 0 to a 1. So if we have A with a value of 1, then a bitwise not of A must therefore be 0. And if A has a value of 0, then a bitwise not of A must therefore be 1. And again, you can think of this like changing it from true to false, or from false to true, similar to how the Boolean operations work. And we can always look it up in the truth table to see what the values are. So that is how the inversion works. But let's have a look at how and or work. These are very similar, again, to the Boolean operations you know, except again, these are going to work on numbers. So if A and B are both 0, that is A and B are both false, then the result of the bitwise operation A and B is false. And this is just like it is in Boolean algebra, right? False and false is false. And so you can see the parallels between what you already know and what we have here. For A and B to be true, for it to be 1, both A and B have to be true. And we see that at the bottom of the A and B truth table there. Likewise with or, you've seen this behavior before with Boolean algebra as well. So we have A or B the result is true if either one or the other or both of them are true. So if A is 1 and B is 1, A or B is also 1. And it's interesting because we're thinking about this from a sort of a true-false standpoint, with 0 being false and 1 being true. But again, we're using numbers here. We're saying these are mathematical operations that work on numbers. So a quick peek here with and. the bitwise AND operator is an ampersand, a single ampersand. You're used to using double ampersands for Boolean values, but this one is a single ampersand for bitwise. And once again, don't use one when you mean the other. If you're working with Boolean values, true or false, then use the double ampersand. If you're working with numbers, then use the single ampersand. So here's an example. A and B are both 0. We know from the truth table that 0 and 0 is 0. So that's the result for here. If A is 1 and B is 0, then the result for A and B is it's also 0, because they both must be true for the result to be 1. So here we have A is 1 and B is 1, and indeed, if they are both 1, then the result is 1. Similar to the AND operator, we have the OR operator. It uses the pipe symbol. Again, with Boolean, you use two pipes, the double pipe, but with bitwise, where we're dealing with numbers, we only use the single pipe. So A is 0 and B is 0. A or B, well, if they're both 0, then the result is 0. If one of them is 1, then the result is 1. And if both of them are 1, the result is also 1. So if we have a look back here, we can always see that this is the truth table demonstrates this to us. So with the OR operation, if either A or B is 1, then the result of the operation A or B is also 1. Or if both of them are 1, then the result of A or B is also 1. Now we've seen NOT for inverting the value, and we've seen AND and OR and what those do. There are a couple of relatives of AND and OR, and they are called NAND and NOR. And in this slide, we have our friend A and B on the left, just like we had before. So that's a regular A and B, just like you know. They both must be 1 for the result to be 1. On the right, we have NAND. And all this is an inverted AND. It means not AND. That's what the N is for. But if you look at the result column of A and B on the left versus the result column of A NAND B on the right, you see that they are simply inverted. Every place there's a 0 in the A and B column on the left, there is a 1 in the A NAND B column on the right, and vice versa. So it's just like an AND, except inverted. So how can we do this in C code? Well, it's a little bit different, because in C and other C-like languages, there's no NAND operator. But we can make it. We can make one with an AND and a NOT, because NAND is not AND. First we do the AND, and then we invert it at the end. So that's what we're doing here. So if we have A is 0 and B is 0, first we do the AND in here, and then whatever the result of that is, we invert it. So in this case, A and B is 0, because they are both 0, and then we invert it, and that becomes 1. And here, A and B is also 0, because A and B must both be 1 for the result to be 1, but B is 0, so the result of A and B is 0. And then we invert it with a NOT, so 0 inverted is 1. A NAND B, here we go. So here A and B is 1, because A and B are both 1, and so we invert it with the NOT, and we end up with 0. So that's how NAND works. There's also a NOR, but it works very similarly to the NAND. I'm going to just leave that up to you guys to think about how we might want to do NOR. If we've done NAND this way, by building one out of tilde and ampersand, like this, you might use that as a template to figure out how to do NOR, which is not OR. And we do have a truth table for NOR, which is here. So your usual truth table for A or B is on the left again. So if either one or both is true, then the result is true. And then we have the table for A nor B on the right. And you see in the result column That is the exact inverse of the result column on the A or B table. Exact same operation, just inverted at the end. Similar to the other bitwise operations, but kind of cool in a novel way, is XOR, or exclusive OR. So exclusive OR is just like OR, but it's only true if either one or the other is true, not both. So we see in this truth table, unlike the truth table for OR, we see that if both of them are true, then the result is not true. It's only true if one or the other, but not both is true. And XOR, the XOR operation in C-like languages is represented by the caret. And so we can use that to do an exclusive OR operation between two numbers. So, if A and B are both 0, then A exclusive OR B is also 0. Only one or the other can be true for it to be true. But here, neither of them are true. Likewise, what we have here, A is 1 and B is 0. That means one is true and the other isn't. That is the success case for an exclusive OR. So for this exclusive OR, we get a 1 result. In this case, they're both true. So if this were A or B, the result would be true. But it's A exclusive OR B, which means only one of them can be true, which means the result of this operation is false. So that is a quick survey of all the different bitwise operations we have at our disposal. But what we can also do now is do some work with multi-bit numbers. And we can show how that works. Everything we've done so far has been with a single bit. Turns out with multi-bit numbers, it's actually pretty straightforward what you have to do. So if we have a multi-bit number and we want to perform a certain operation on it, I'm just going to make up a multi-bit number there, and we're going to do an AND operation. And we'll add a different multi-bit number there. So we want to add these two numbers together, two binary numbers. And two binary numbers together. And the way we do that is one bit at a time. And we look at each column in isolation. It's just like if we were adding them together or something, except we don't have to worry about carrying results or anything like that. We just look at each individual bit in isolation. And so for this bit in this column, we have 1 and 1. And if they're both true, we know the result is also a 1. And then we check the next column here. In this column, we have 1 and 0. We know that with AND, if one of them is false, the whole thing is false. So we put a 0 for that column. Likewise, the next column, 1 and 0 is 0. The next column, 0 and 1 is 0. The next column, 1 and 1 is 1. 0 and 1 is 0. Again, we were just looking at the two numbers in this column here and performing the operation on them. 1 and 0 is 0, and 1 and 1 is 1. And that's how you do multi-bit numbers with all the different operations. Another example might be, I'll make a random number here, and then we'll do an exclusive OR operation with a number like this. And again, it's exactly the same technique. We're going to do an exclusive OR between each column of numbers here. And remember, exclusive OR is true if either one or the other, but not both are true. So for this column, the result is 0, then 0, then 1, then 1, then 1, then 0, then 0, then 1. For this, again, we've just done every single column. 1 XOR 1 is 0, 1 XOR 1 is 0, 0 XOR 1 is 1. This column, 0 XOR 0 is 0, and so on. So this is the same for all of the bitwise operations, and or exclusive OR. You just do the individual bits one at a time. And has one interesting property here, which can be demonstrated with another example. I'm going to AND with this value here, and I'm going to use this as something called a mask. And this allows you to extract individual bits from another number while preserving some and removing others. So with the AND operation, anywhere there's a 1 in this number, the values up here will be preserved. And anywhere there's a 0, the values up here will be eliminated. And it's kind of easy to see that this is true with a little bit of reflection, because if you AND 1 with 0, you end up with 0, which is what you started with here. If you AND 1 with 1, you end up with 1, which is what you started with in this for top number. So any time you AND 1 with another value, you end up with that other value. Whereas anytime you AND 0 with another value, you just end up with 0. So this mask will preserve the topmost number wherever there's a 1, just like we have here. 1101 has been preserved here, 1101. And then the rest of the number gets turned into zeros because it has been masked out. Now there's one more operation we can talk about very briefly, and that is shifting. You can also shift numbers left or right when you have a multi-bit number. And the left shift operator is less than, and the right shift operator is greater than. And what these do is actually move the bits of the number left or right. So if I have a number such as, I'm going to leave some off here, we'll just say 1111, and I want to shift that left 1 bit, you can actually do that and end up, I'm going to draw left shift by 1 right here, and that will move the entire thing 1 over to the left. So there's our 1111 that we had, and there's a 0 put in the end. You could shift it by 2 bits or 3 bits at the same time if you wanted. And it just fills in zeros for the new bits. Likewise, you can shift right. And when you do that, the bits that shift to the right just fall off into nothingness and vanish forever. So if I had a number, again, like 1111, and I do a right shift by 1, then this simply turns into 111, and then the last number that was here, that last bit, just gets shifted away into nothingness. So the last 2 operators there, left and right shift, for moving bits to the left or to the right. And with all these things, this actually gives you enough power to manipulate individual bits, to set bits to true or false individually, or clear them, or set groups of bits, and so on. So a lot of power is put together in all these bitwise operations. So going forward, here are some challenges that you can do. And I'll just let you pause the video here. Look at these things. We've covered enough material in order to solve all these challenges for this video, and see if you can figure them out. Thanks for watching.